This is what Gradescope looks behind the scenes. So this is the dashboard that lets me see how many people have submitted homework and what progress is like on grading and so on and so forth. So in particular, you can see that already half of problem 1 and homework 0 has been graded, even though the homework was submitted, 40 hours ago. And people are already starting to make progress on problem 3. One thing that I do want to point out here, officially there are exactly 300 students registered for this class, because that's the capacity that we can support with the TA staff that we have. But less than 300 students have submitted all of homework 0. In fact, not all 300 students even submitted problem 1. If you didn't submit homework 0 because you're still settling in, something, you're just, the first couple weeks of any semester are chaos, and so it just didn't happen this time, not a big deal. The way the homeworks are weighted into your final grades is flexible. We automatically drop a couple of the homework assignments anyway. If you skip another one, it just means the exams will count 1% more in your final grade. Really not such a big deal. On the other hand, if you're one of the 20 people who didn't submit all of homework 0, and it's because you're really thinking that this is not the class you want to take this semester, I hate to see you go, but if you're going to leave, if you're going to drop the class, there are other people waiting to get in. So, and it becomes much more difficult for those people to get in after next Monday, which is the official add deadline. So if you are strongly considering dropping the class, please come talk to me, either immediately outside after the class or in office hours this afternoon. But if you've already decided that you're going to drop out, please go ahead and do that so that other people who are trying to get into the class can get in. If you do decide to drop, you are still welcome to come and sit in on the lecture. You are still welcome to, if you really want, submit homework to Gradescope, because we don't actually know who you are on Gradescope. We can't tell. I suppose I could figure it out, but I'm not going to. You can still get feedback on these things if you submit them, because maybe 1 or 2 people a semester actually do that. It's not such a big deal to grade 282 things instead of 280. So you can think of this as, if you decide that you want to drop the class now and take it next semester, you can think of this as a dry run. Keep coming to lecture, keep going to labs as long as it fits with the rest of your schedule. But because there are other people sort of waiting, I want to try as much as possible to get them in without having to set up this period of multiple weeks of waiting. Can we get in yet? Can we get in yet? Can we get in yet? Which is why I'm not running a waiting list this semester as I have in the past. I think I said this in the first week of class, the last time I ran a waiting list, people didn't get in until like well after midterm 1, which just stressed everybody out, including me. So there's progress. I'm hopeful that most of homework 0 will be done by the middle of next week. We will release the homework scores problem by problem as soon as they're graded. So it's not like we're going to wait until all of homework 0 is done before we release the homework 0 grades. We're recording all these things independently, in part so we can be a little bit asynchronous. Okay, that's all I wanted to say about that. Homework 1 is out. And I do want to emphasize with homework 1, especially for problem 2, start now, actually start yesterday, because problem 2 is hard for 2 different reasons. One of the reasons that problem 2 is hard is that it's just technically difficult. The tools that you'll need to solve this problem, or the best way to solve this problem, we're going to talk about today in this lecture. Okay? But the other reason why this problem is hard is because the solution is somewhat complicated. That means it really requires very careful attention on your part for how you write down your solution. Remember that your goal is not merely to come up with the right answer. Your goal is to come up with a convincing explanation of the right answer for another human being. And those two are very different goals. And the second one is really insufficiently emphasized in the rest of the CS and CE curriculum. So we are really going to be paying attention to, are you explaining this precisely, unambiguously, but also clearly? Which may mean you need to think about 2 or 3 different ways of naming your variables, and 2 or 3 different ways of organizing the explanation, and 2 or 3 different ways and picking out the one that actually works the best, talking to each other, saying, well, we kind of got the same solution, but how did you say it? And how did I say it? Which one of these actually works better? And converging on something that clearly communicates this. And I mean this, I wish this were inculcated into people much earlier. When you write code, you are not primarily communicating with the compiler. You are primarily communicating with the next programmer, another human being. This is why you write mnemonic variable names and mnemonic function names, and why you comment your code, and why you organize things modularly, and why you reuse things, is because somebody else is going to be stuck reading and trying to understand your code. This is the thing that we're pushing at here, first and foremost. There's a point here that, reveal that this is a DFA design question where the smallest DFA for this language has 20 states. I have not been able to come up with a legible drawing of this DFA, so don't try. Right? We need to express these things formally using the tools that I'm going to talk about today. This is not something to start on Friday evening. Start soon. Okay. So on Tuesday, we started talking about DFAs, deterministic finite automata. Finite meaning that these are devices, machines, abstractions with a finite number of states. Automaton meaning things happen on its own. This is really an abstract model of a machine. Deterministic means every time you run it, it does the same thing. The behavior is completely determined by this transition function that's part of the DFA. So just to remind you of the definitions of what a DFA is, formally, it has a set of states, it has an alphabet, it has a start state, it has a set of accepting states, and it has a transition function. So the states are an arbitrary finite set. The input alphabet is a different arbitrary finite set. S is the start state. It's an element of Q. A is a subset of the states. These are the accepting states. And finally, delta is a function that takes a state and an input symbol and gives you a new state. This is what's called the transition function. And then we extend the transition function from individual symbols to strings recursively by basically expanding the recursive definition of strings. So given a state and a string, I get a new state. And this is defined by saying the starting in state Q and given input W, I'm either going to stay in state Q if W is the empty string, or I'm going to transition from the state you get to following the first symbol from Q, and then recursively following the rest of the input string, which here I'm calling X. And then finally we say M accepts W. What that means is that delta star of SW belongs to A. Okay? This is all just a reminder of what we did, the formal definitions of what we did on Tuesday. Now, at least for fairly simple things, most of the time you're not going to be dealing with things that look like stacks of Greek letters in parentheses. Most of the time you're going to be dealing with a representation of the DFA that looks something like this. Now, ignore the specifics here. I'll explain exactly what this DFA is doing in a second. But the thing to take away from this is you have a drawing of the DFA as a directed graph, where you have a node for every state. So you have some finite number of states. You just represent each one by a circle on the paper. You have an arrow coming into the specific state that you want to identify as the start. You double the boundary of any states that you want to recognize as accepting. And it's perfectly okay. And we saw an example last time where the start state was actually one of the accepting states. So you can have both. There isn't necessarily only one accepting state, but in this example there happens to be. And then for every state, there is an outgoing arrow labeled with each of the input symbols. So in this case, the input alphabet is 0, 1. And so for every state, take this one in the middle left, there's an arrow going down labeled 0 and an arrow labeled up and going up and to the right labeled 1. And the semantics of this are, you imagine putting your finger, and if you draw this on paper or on a blackboard, I strongly recommend actually taking your finger and actually putting it on the board and following along. I read a 0, and then I read a 1, and then I read a 1, and then I read a 1, and then I read a 0, and then I read a 1, and then I read a 1, and then I stop because I ran out of input. Because I landed in this state that was not an accepting state, that input string is not accepted. Okay? Let me move this down so I can actually do this again. So again, starting here, if I look at the string, I don't know, 0, 0, 1, 0, 1. Okay, so I started S. This is my start state. 0, 0, 1, 0, 1. That string is not accepted by this DFA because I didn't land in an accepting state. On the other hand, if I said 1, 1, 1, 1, 0, 0, 0, I would go 1, 1, 1, 1, 0, 0, 0. And because when I ran out of input, my finger was on a doubled circle, that means that that string is accepted by the DFA. Okay? This is the most common way of writing down a DFA, but it's not the only way. Sometimes it's actually saner to write down a formal description where you define the transition function delta using some kind of mathematical notation. It may make more sense to write down the transition function delta as just a table, if that's more sensible than trying to draw the graph, especially because a lot of graphs you can't draw in the plane without having edges crossing over each other and making a big mess. But this is the one that you're probably most familiar with, and probably the one that you played with the most in the lab yesterday. So part of what I want to talk about today are other ways of manufacturing DFAs, and in particular of taking small DFAs and combining them to get larger DFAs. Okay, so this picture is an example of the kind of thing that we'd like to be able to do. So let me focus in on just this DFA here on the top. Okay. This DFA has 3 states. Can anybody tell me what language this DFA accepts? Yes. Right. Any string that has 2 ones in a row. This is, in fact, the example that we ended class with on Tuesday. Okay? So we have a start state, which we're in if I didn't just read a 1. Either I'm starting out or I just read a 0. I have this state A, which I'm in if the last symbol I read was a 1, but the one before that wasn't. And then finally, I'm in state, and I've never seen a 1. I've never seen a 1-1. And finally, the state B is, I've seen a 1-1. I know I'm going to accept. Again, because this came up both during and after class, I want to emphasize, even though at this point we know we're going to accept, the DFA has to continue until it finishes the input. So I have to define these transitions that just idle. Okay. Now let me go over to this DFA. It's really similar, but it's not exactly the same. What does this DFA recognize? Yeah. Exactly, 2 zeros in a row. And the only differences between this DFA and the one I showed you before is that I swapped 0 and 1 on every edge label, and I rotated it 90 degrees. Obviously, the rotation doesn't matter, but I drew it vertically instead of horizontally. And the reason I did that is because of this big construction in the middle that I'm about to show you. Okay? So without, I'm just going to show you the example and see if you can figure out what this thing in the middle actually is. Anybody guess what this 9-state DFA accepts? That's right. This accepts the set of all strings that contain 2 zeros in a row and 2 ones in a row. Now, if you think back to when we started talking about DFAs, I said it's sometimes useful to think about these things as algorithms. And you can imagine running, you have a big for loop and you have some local variables that take on a finite number of different values. But you can imagine taking an algorithm that recognizes, hey, are there any 1-1s in this input string? And another algorithm that says, hey, are there any 0-0s in this input string? And interleaving them. For I equals 1 to n, do the thing that the first state would do, and then do the thing that the second state would do, the second machine would do. And now you have an algorithm that takes the variables from the first algorithm and the variables from the second algorithm and combines them into a single algorithm that checks both conditions and returns some Boolean combination of these things. Because you can think of the 1-1 DFA as an algorithm that has a single variable that can take on 3 different states, 3 different values. And I can think of the 0-0 DFA as an algorithm that has a single variable that can take on 3 different values. Now, if I put these together into a single algorithm, I now have an algorithm that has 2 variables, each of which can take on 3 different values. A state of that algorithm is what value does the first variable have, and then independently, what value does the second variable have. So I have 9 different possibilities for the internal state of this new combined algorithm. Every state corresponds to a state in one factor and a state in the other factor. So this is commonly known, this kind of construction is commonly known as a product construction. I'm taking 2 DFAs, each that recognize its own language, And by combining them, I'm producing a new DFA that recognizes the intersection of those two languages. I have a DFA that recognizes 1-1s, a DFA that recognizes 0-0s. The new DFA accepts a string if and only if it's in both of those sets, so it recognizes the intersection. Yes? The point of defining state A is I'm about to give you a mechanical recipe for this product construction, and this is what the mechanical recipe produces. I don't actually need this, and like other mechanical recipes, I'm not guaranteed to get the smallest possible DFA. So for example, if I said, take a DFA that recognizes strings containing 2 zeros in a row, and take another DFA that recognizes strings with 2 zeros in a row, and make their product, I'm intersecting the language with itself, but nevertheless, I'm still going to get a 9-state DFA. Okay? So there may be some redundancy in what the product construction gives you, but once we have it, then we can play around and maybe make things a little bit simpler. Okay? So in general here, the idea is that the states of the new machine are pairs of states, one from the first machine and one from the second. This is just the definition of the product of two sets. You can write this as Q1, Q2, where Q1 is a state from the first machine and Q2 is a state from the second machine. Okay. The input alphabet's the same, right? I'm combining two machines with the same input alphabet, so I'm not going to write down the input alphabet again. It'll be the same thing. I need to specify a start state for the product machine. And in general, that's going to be the pair where the state from the first machine is the start state, and then the other element of the pair is the start state from the second machine. In this case, because I'm looking for the intersection of two languages, okay, so a state is accepting, well, first of all, it has to be a state. So it's an ordered pair consisting of a state from machine 1 and a state from machine 2. But these states have to satisfy certain conditions. So can anybody guess what those conditions are? I'm trying to accept strings that are accepted by machine 1 and strings that are accepted by machine 2. How should I define the accepting states of my new DFA? Yes, in the back. Yes, exactly. Q1 is an accepting state of the first machine, and Q2 is an accepting state of the second machine. Okay. This is actually really important. And in particular, it's really important to specify explicitly, because there are other things that I can do with this instruction, this construction. And then just to be consistent, I really should do that with the states as well. And then finally, actually, I'm going to do something I should have done a little bit earlier. I'm going to make some room for myself. Don't panic. Don't panic. Don't panic. Okay, panic. All right. Anyone interested in HCI? Don't do that. I also now need to define a transition function for the new machine. Okay, and the transition function, remember, is a function from states and input symbols to states. So the input to my function is going to be a state that is a pair Q1, Q2, and an input symbol. The output of the transition function is a state of the new machine. That means it's an ordered pair consisting of a state in machine 1 and a state in machine 2. But what are those two states? Okay, so I think maybe it would be good to actually follow along here. Let's suppose I'm going to emulate the machine on the string 1, 0, 0, 1. Okay? So the machine that's looking for two ones in a row, it's going to go 1, 0, 0, 1. The machine that's looking for two zeros in a row, 1, 0, 0, 1. So what's going to happen is this. 1, 0, 0, 1. Okay? Now, you probably can see what I was doing because I'm in the way, but, and I'm not good enough to actually do it like this. But what I want you to imagine now is what it means to be in this state is that my left finger is on here and my right finger is on there. Right? So when I did this dance, when I was, say, here, that means in the product machine, I'm there. Okay? So 1, 0, 0, 1. Now I'm in the product state, I'm in state B, comma A. That means I'm in state B, the machine on the left, and I'm in state A, the machine above. So if I'm in this state, B, comma A, and I read a 0, where do I go? Well, the left machine stays put, and the top machine moves to the left. So down here, I will go from state B, comma A to state B, comma S. Okay? Now, how do I write that down formally? I need to write down these two components of the new state. Yeah. That's exactly right. The first machine transitions from state Q1 on symbol A, and the second machine transitions from state Q2 on symbol A. The point is that the product machine is really just emulating the two smaller machines running at the same time. A state for the product machine is a state of this machine and a state of that machine, specified independently. So when I transition in the product, that means I'm transitioning in both of the smaller components independently, using exactly the same inputs. This is just how you write that down. Okay. All right, let me clean this up a bit. By the way, the other way that I could have written this is the set of accepting states is A cross A. This is the same definition. Okay? Yes, sorry, A1 cross A2. Thank you. Okay? So I have given you an example and sort of walked through the example to try to extract some general formalism of how you would combine two DFAs. So if I have a DFA that accepts language A and a DFA that accepts language B, I want a DFA that accepts the intersection of those two languages. String that should be accepted if and only if it's accepted by the first machine and it's accepted by the second machine. This intersection means and. That's why the symbol for and the symbol for intersection, I'm sorry, the symbol for intersection and the symbol for and both have legs downward, both pointing the same way, because they're the same operation. Similar constructions will work for other Boolean combinations of languages. So, for example, this is how you would accept a string that either has a 0, 0 or has a 1, 1 or both. This is accepting the union of the languages accepted by the two machines. And the difference is only in the specification of the accepting states. Right? Here, in this product, the state is accepting if and only if either the first component is an accepting state of the first machine or the second component is an accepting state of the second machine. Yes? Yes? In this particular case, yes. You could collapse all the accepting states into one for the same reason as the example we saw on Tuesday, where once I'm in an accepting state, I'm always going to be in an accepting state. So I've already made up my mind to accept. Why do I need to keep track of anything else, right? But you'll notice, for example, for the second one, you can't do that. The second one is exclusive or symmetric difference. Here, I want to accept strings that contain either a 0, 0 or a 1, 1, but not both. And now the specification of the accepting states is a state Q1, Q2 is accepting in the new machine if and only if Q1 is an accepting state in machine 1, exclusive or Q2 is an accepting state in machine 2. The last one is, make sure I get this the right direction, because this is an implication. So if it contains 0, 0, then it contains 1, 1. Or said differently, either it doesn't contain 0, 0 or it does contain 1, 1. And then Q1, Q2 is an accepting state if and only if either Q1 is not an accepting state of machine 1 or Q2 is an accepting state of machine 2. Or said differently, Q1, Q2 is an accepting state if and only if Q1 is accepting in machine 1, then Q2 is accepting in machine 2. This is essentially like a set difference operation. Right? So I want all the things that do contain 1, 1, except for the ones, or sorry, do contain 0, 0, except for the ones that don't contain 1, 1. No, I'm just going to think of it as an implication. I'm just going to confuse myself if I try to translate this into sets. So the important thing is here, I'm defining different ways of combining Boolean operations on sets. And for any Boolean operation you can imagine on a pair of languages, there's a corresponding way to combine the DFAs for those two languages into a product DFA that accepts that Boolean combination. Yes? So the output of the product construction contains all states, all 9 of these states. Once you have the output of the product construction, it's a DFA. You can collapse equivalent states. You can get rid of unreachable states, just like you can with any other DFA. So why would I want to keep those redundant or unreachable states around? Because describing the machine may become much more complicated if I work harder to reduce the number of states. right? In this case, I can literally just describe the DFA by saying, well, I have this DFA that recognizes strings with double zeros, and I have that DFA with strings that recognize double ones. I compute a standard product construction where the accepting states are these. Done. Whereas, if I said this state AA is redundant and I want to take it out, suddenly, in order to describe the new DFA, I have to explain what each of those 8 states actually means. Instead of just saying, I wrote this subroutine and I wrote that subroutine and I called them both, you somehow merge them together and now you have a more complicated thing because you've made it more efficient, and that made it more complicated. So there is a trade-off between the efficiency of the machine that you're building and the efficiency of your description of that machine. I will again refer you to the last paragraph of question 2 on homework 1. It is generally better to aim to be clear than it is to aim to be fast. And we're going to see this again when we get to algorithms. The primary thing is we're going to want our algorithms to be as fast as possible, but you don't want to spend time making small optimizations if it makes the description much more complicated. Okay? All right. So, here's the definition of my product machine, right? And so my claim is if M1, actually, let me just write it this way. The language accepted by this machine is equal to the language accepted by M1 intersects the language accepted by M2. Right? And I'm claiming, this is a claim that I'm making regardless of what the component machines M1 and M2 are. So maybe it's clear from the 9-state example, but in order to justify this in general, I really have to give you a proof. And what this ultimately boils down to, the key lemma, everything else is just going to be definition chasing, is that if I start in a state PQ in my combined product construction DFA, and I transition based on some input string W, what do you think I'm going to get? Well, I'm going to get a state, which is a pair of state from M1 and state from M2, but what state would you expect to get to in M1? Right, delta 1 star P W. In what state would I expect to get to in machine 2? Thank you. So when I was a master's student, somehow never had anyone do this to me when I was an undergraduate. When I was a master's student, I had a professor who said, occasionally I'm going to ask, are there any questions? I'm going to ask you a question, and I'm going to wait for a response. Often people don't want to talk because they think there's a trick question and they're worried about being embarrassed. I want to make it very clear that there are no stupid questions. Don't worry about being embarrassed. Saying the wrong answer is fine, then we can explain why the answer is wrong and we can move on, we can learn from it. But it's very hard for people to put themselves out in front of a crowd of people. So often what happens is I'll ask a question and it'll be nothing. But over the years, I've learned to be very, very patient. After about 10 seconds, it starts to get really uncomfortable. After about 20 seconds, people are squirming in their chairs. I've never had to wait more than 30 seconds. but I'm willing to try. So occasionally I'll ask you things. Please, when I ask, are there any questions? Please don't be afraid to ask a question that you think the answer is obvious and you just didn't get it and everybody else in the room already understands and you don't. Believe me, if you have a question, there are 40 other people in the room that have exactly the same question and will be thankful that you were the one to ask it. Okay, so are there any questions about the statement of this lemma? Ten. Apparently not. Good. You all get it? Awesome. If a question occurs to you later, please hold up your hand. Okay, so this deserves a proof. And anyone care to guess how we're going to prove this? Let me try that again. Anyone care to guess how we're going to prove this? Thank you. Why do I know it was induction? Because we did induction last time. All right, so let W be an arbitrary string. I suppose I should also say let P and Q be arbitrary states in their respective DFAs. Now I need an induction. Oh, wait. Thus, delta star of PQ on W is equal to delta 1 star PW, delta 2 star on QW. I want to get ahead of myself. Assume for all x shorter than W that actually, I think I need to be a little careful, and all states P prime, Q prime, again from their respective DFAs, that P prime, Q prime on X is P prime on X, Q prime on X. I'm thinking ahead a little bit here because I know that if I transition on the first symbol of W, I'm likely to end up in a different state in both machines, so I need to name that other state. And here I'm looking ahead to the recursive definition of W as either the empty string or symbol dot a string X. So there are two cases. What are the two cases? W is the empty string, and the other one is W is not the empty string, which means that W is some symbol A followed by some string X. All right, so if W is the empty string, then delta star of W comma epsilon is, or sorry, not W, delta star of PQ comma epsilon is by definition PQ. This is just part of the definition of delta star. Right? The base case in the definition of delta star says if you read the empty string, you don't change state. But this is equal to delta star P epsilon, delta star Q epsilon, again, by definition of delta star. Yes? Arbitrary, sorry. Sorry, I should be a little careful with my handwriting. And I'm not writing down, I mean, P is a state of M1 and Q is a state of M2. P prime is some state in M1 and Q prime is some state in M2. We'll get there. Okay, so then the next question is, what do we do when W is equal to symbol A followed by string X? So again, I'll write down the definition. PQ, comma, AX. This is equal to delta of PQ, comma, A applied to X. This is, again, recursive definition of delta star. And now this is delta star of delta P comma A, delta 1 P comma A, delta 2 Q comma A, all that comma X. This is the definition of the product transition function delta. Replace this expression with its definition. Now, at this point, I want you to think of this as P prime, and I want you to think of this as Q prime. P prime is a state in machine 1, Q prime is a state in machine 2. And now by the induction hypothesis, I can rewrite this as what does the induction hypothesis actually say? This is delta 1 star of delta of P comma A applied to X, comma, delta 2 star of delta 2 of Q A applied to X. And I've got too many closed parens here. And at this point, I'm basically done because this is the same as delta 1 star PW, and this is the same as delta 2 star QW. This is all in the notes. If you've been frantically scribbling this down and you missed a step, it's explained with all the, much more neat typing than I can do with my hands, with all the reasons spelled out in the lecture notes. But this is really just another exercise in inductive definition chasing. Okay? So this tells me that this extended transition function, the transitions behave the way, of course, we would expect them to behave. If I say the way I transition on a single symbol is I look at how each machine transitions on that symbol and I take the result. What this is saying is that implies that if I want to know how the product machine transitions on a string, it follows around, what I should do is look at how it transitions in the first machine, look at how it transitions in the second machine, take the results and just put them back together. Now, it's useful, again, if you want to get some more intuition about this, to take this thing and put it on a piece of paper and literally walk around with your fingers on the states of the top and left machines and watch with your third finger how the machine moves around in the middle. If you can do this or something, or put a pencil on your mouth and do that. Or use, 2 pennies and a nickel or something. But I'm actually quite serious about this. You actually do this, print out a physical artifact and actually interact with it physically with your hands. Don't just do things on the computer. Don't just do things with the abstraction. It's really helpful to get the intuition in your hands in a way that just playing with the symbols won't get. And then the rest of the proof that the languages are the same boils down to the definition of the accepting states. And again, more definition chasing that I don't want to do. But the key observation here is this inductive recursive lemma that says, well, I have these two recursive function definitions. They combine in exactly the way you think they do. Okay? In the lab on Friday, tomorrow, you'll be asked to apply this definition. So we're going to ask you to design machines that do this and that. Those machines that we're going to ask you to design are right on the edge of where you might want to draw them, and you might want to think about them formally in terms of these definitions. And that's deliberate because really I want you to try to interact with them both ways. Okay. The think about them later questions, formalism. All right. Now, one of the things that this implies is that if I have two languages, L and L prime, that are recognized or accepted by DFAs, which in the notes I refer to as the language is automatic. A language that's accepted by a DFA for the next 10 minutes I'll refer to as an automatic language. Then L intersect L prime, L union L prime, L minus L prime, L symmetric difference L prime are also accepted by DFAs. Okay. And as a particular special case of this observation, in particular this one, this implies that in particular sigma star minus L is accepted by a DFA. Because I can build, it's easy to build a DFA that accepts sigma star. It has one state, it's the start state, it's the accepting state, all transitions loop back. That accepts every string. So there's a string, there's a DFA that accepts sigma star, so if there's a DFA that accepts L, there's a DFA that accepts the difference between these. This is normally written as this is the complement of the language L. Okay, so Boolean combinations of automatic languages are automatic. Now, previously, we thought about a different set of languages than L union L prime, L concatenate L prime, and L star are regular. And so we have a vocabulary of ways of building automatic languages out of other automatic languages. And the definition of a regular language gives us a different vocabulary of ways of combining regular languages into other regular languages. The nice thing about this formalism is that these two sets of languages are actually identical. A language is regular, meaning a language can be described by a regular expression if and only if that same language is accepted by some DFA. If I build a DFA, that means there is a corresponding regular expression. If I build a regular expression, that means there is a corresponding DFA. Now, I will invite you to think for a moment, very briefly, about how you would prove that the intersection of two regular languages is regular. I give you two regular expressions, and now I say, go make me a regular expression that accepts only things that are captured by both of these. You're not going to have an easy time of this. And one of the reasons for that is a regular expression that matches this intersect that could be exponentially longer than the regular expressions you started with. Similarly, Think for a little bit about how you would take a DFA that recognizes the language L and try to turn it into a DFA that recognizes L star. Again, you're going to have trouble with this partly because if your original DFA for L had n states, your new DFA for L star might have exponential in n states. There's not a simple thing the way there is. I mean, union here is, for regular languages, union is just by definition. For automata, union is by building its product construction. But there isn't a similar product construction that would give you L star, or even L concatenate L prime. But if you know that these are equivalent, if I'm given two languages and I want to know, I say these two languages are regular, the reason I know that their intersection is regular is because I can say, well, take your first language L, build a DFA for it, call that M. Take your second language L, build a DFA for it, call it M prime. Now, if standard product construction gives me a third DFA that accepts the intersection of these two languages, and because I have a DFA that accepts the intersection of these two languages, I know that there is a regular expression representing the intersection of these two languages. Therefore, the intersection is regular. I'm not explicitly constructing it because I haven't told you how to make the equivalence between regular and automatic constructive. For now, I just want you to accept that these are two different ways of defining the same family of languages. Okay? Language is regular by definition if it's described by a regular expression, but by theorem if it's describable by, if it's accepted by some DFA. We will prove this next week, but we need a couple more tools before we can launch into the proof. Now, one of the things that this equivalence gives you is it's actually possible to show that a particular language is not regular by proving that there is no DFA that accepts it. And the core of the proof is in arguing that if I can stare at the language and I can somehow prove that any state machine that accepted this language needs an infinite number of states. It's not a DFA, it's a DIA. DFAs have to be finite. Finite state machines have to have a finite number of states, right there on the label. If I can show that I need an infinite number of states, meaning no matter what number you give me, I can prove that I need more states than that. Then this is a way of showing that the language isn't regular. So what I want to do in the last 20 minutes, we actually have 20 minutes this time, is show you how to walk through an example and show you how to prove that a language can't be accepted by a DFA. The way you prove it can be accepted by a DFA is you build the DFA, or you build the regular expression, or you argue that it's some combination of other things that you already know can be accepted by a DFA. Right? But if I want to show that something isn't regular, I need to work a little bit harder. Okay? So before I go on, are there any questions about the statement that's on the screen about combining languages? These are not the only ways to do this, by the way. There are other combinations that will also work. L and L prime, so what I mean is, when I say that a language is regular, the definition of that is there is a regular expression that represents that language. When I say that a language is automatic, the definition of that is there is a DFA that accepts this language. And the claim that I haven't proved to you yet is that these two adjectives are synonyms. Regular and automatic are the same thing. L and L prime here are two different languages that happen to be in this category. So maybe L is all strings that contain 1, 1, and L prime is all strings that contain 0, 0. Okay? All right. So let me throw up an example DFA for you. Zero, 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 1, 1, 1, 1. Right. And just as a sanity check, can you tell me what this DFA accepts? Yes. Right. Any string that has an even number of zeros and has an odd number of ones. If you're paying attention, you'll notice this is a product construction of two machines, one that accepts all strings with an even number of zeros, and the other that accepts all strings of only ones but an odd number of them. Okay, so let's look at two strings here, 0, 0, 0, 1, 1, 1, 0, 1. Okay, now, if I start in the upper left corner and I transition according to both of those strings, let me label these states here, even, even, odd, even, even, odd, odd, odd. Right, delta star of S, that's even, even, delta star of S. This, in both of these cases, I'm going to end up at odd, odd. Okay, so 0, 0, 0, 1, I'm going to go 0, 0, 0, 1, and 1, 1, 0, 1, 1, 1, 0, 1. Okay? Now, what this means is that if, notice what happens if I write suppose I happen to know that for some string x, some specific string x, I don't know, 1101101111111011. I'm not going to remember that, so let's call it x. I happen to know that 001x is in the language. 001x has an even number of zeros and an odd number of ones. What can I conclude about the string 1101x? It's also an L. And the proof is, if I run this machine on 0001, I end up in that state in the bottom right corner. If I run the machine on the string 1101 starting from the beginning, I also end up in that lower right corner. So from here on out, I'm reading the same symbols, the ones in X, starting at the same state, and so I'm going to end at the same state. And because there's only one accepting state, if the first string lands in that accepting state, then the second one must land in that accepting state also. And in fact, this is an if and only if. If the first string does not land in an accepting state, then the second string does not land in an accepting state either. Okay? So this is an example of a more general statement. Okay? So for any language L, for any strings X and Y, and I really mean any strings X and Y, not any strings X and Y in L. Any strings at all. Okay? If there is DFA such that X and Y lead to the same state, then for all strings Z, XZ is in L if and only if YZ is in L. Okay? So pick your favorite language and build a DFA for it. I should say there's a DFA that accepts L. Sorry. Okay. There's a DFA that accepts this language. L and X and Y lead to the same state in that DFA. That means no matter what string I follow X with or I follow Y with, XZ and YZ are still going to lead to the same state in the DFA. If that's an accepting state, then both of these strings belong to the language accepted by this DFA. If it's not an accepting state, then both of these strings do not belong to the language accepted by this DFA. Okay? So this is saying, this is a test in terms of a single example DFA that tells me something about the structure of the language. And I can plug in whatever DFA I want here as a way of proving this is kind of an equivalence between the strings X and Y. But it's not it's an equivalence, meaning if I glue the same string onto the end of both of them, either they're both in the language or they're both not in the language. And I can prove that X and Y are equivalent by just demonstrating a DFA and saying, look, X goes to the state and Y goes to the same state, and this DFA actually accepts my language L. Right, so this is just a way of extending this single example at the top of the screen to your favorite language, your favorite strings, and your favorite DFA. But now I want to do something somewhat counterintuitive. There's this if-then statement here. I want to rewrite it. So I'm going to rewrite this if-then statement. Instead of saying if A, then B, I'm going to write it as if not B, then not A. I'm going to write down the contrapositive. And this will look complicated because I'm doing a bunch of substitutions at the same time. But if you think about this later after class, you'll see the statement I'm about to write really is logically equivalent to the statement that I've already written. Okay, so here goes the contrapositive. If there is a string Z such that XZ is in L if and only if YZ is not in L, meaning exactly one of those two strings belongs to the language, then for any DFA that accepts L, X and Y lead to different states. All right, so these two statements are logically equivalent. Why do I want to do this? Well, often when we're given a language, we're given it in some explicit form. All strings of zeros and ones that represent a prime number in binary. All strings of zeros whose length is a perfect square. All strings of balanced parentheses. All strings with an even number of zeros and an odd number of ones. And based on this description of the language, we can often find suffixes Z that distinguish X and Y. Right? So if I, for example, am given this even-odd language, and I've deliberately now hidden the DFA, let's think about the strings 0, 1 and 0, 0, 1, 1. Okay? It's called the first one X and the second one Y. Is there a suffix that I can glue onto both of these that would distinguish them? That one of the expanded strings has an even number of zeros and an odd number of ones, and the other one does not. So the first string, 0, 1, has an odd number of zeros and an odd number of ones. what would I have to add to it to get an even number of zeros and an odd number of ones? 0. So this belongs to L. But if I glue the same suffix onto the other string, I have an odd number of zeros and an even number of ones. And that's exactly the opposite of what I was going for. This is not in the language, and remember, I was going for even odd. So this is not in the language even odd. What this means is any DFA you design for the language, even number of zeros and odd number of ones, no matter how many states it has, no matter how few states it has, those two strings must lead you to two different states. So in particular, any DFA that accepts this language has at least two states. Okay? And in fact, it has at least three states because neither of those two strings is an accepting string. Right? By giving examples of pairs of strings, I can say, oh, these two strings have to go to different places. These two strings have to go to different places. These two strings have to go to different places. So, in fact, let's think about the following set of strings. Let's see, what is it? 0, 1, 1, 0, 1, 0, 1, 0, and 1, 0, 1, 0. If I'll let you do this offline, you take any pair of these strings, there's a way of gluing something onto the end that shows that that pair of strings must lead to two different states. Okay? This set of strings is called a fooling set. Any pair in this set has a distinguishing suffix. Okay, so for example, we've already seen that 0 distinguishes the first and last strings in this set because the first one is in my language and the second one isn't. Okay? So I have a set of 4 strings, and any pair of those I can distinguish from each other by gluing on the right suffix. That means any DFA for this language has to have at least 4 states. Hey, look, there's a DFA that accepts this language, and it has 4 states. I've just proved, minus details that are in the notes, this is the smallest DFA that accepts this language. In fact, if you push it this hard enough, there's a mechanical, this is the basis of a mechanical algorithm that takes an arbitrary DFA and recognizes which states are redundant and which states are unreachable and folds them up into the smallest possible DFA for that language. Ultimately, what that algorithm is doing is exercising this finding a fooling set where I have a string that goes to each state and showing that all those strings are distinguishable by some have different behavior if I push them further into the machine. So this gives you a way of proving that a DFA can't be made any smaller. But then the last statement, then I'll let you go. If L has an infinite pooling set, then L is not regular. And on Tuesday, I will show you that, for example, this language, strings of zeros followed by strings of ones where the number of zeros and the number of ones are equal. 5 zeros followed by 5 ones, 10 zeros followed by 10 ones, 72 zeros followed by 72 ones. That language is not regular because I can actually find an infinite set of strings where I can distinguish any pair by some suffix. I think at this point, everybody's brains are full. We're out of time. I'll be up here to answer questions for a few minutes. Otherwise, I'll see you at office hours this afternoon and then on Tuesday. Thank you.
you explain again how you find those Boolean sets? Like that for.
I didn't explain how to do it.
But still, how?
I didn't explain how to find it.
But how did you state that this is a Boolean set? Like how does that match the definition?
Okay, so fooling set means, so for example, if I pick out these two strings, okay, if I 1, 0, 1, even odd, and then I add on 0, 1, as opposed to 0, 1, 0, and then I add on 0, 1. This is in the language, and this is not in the language.
Okay.
So this suffix 0, 1 distinguishes these two strings.
Okay.
I can pick out any pair in the notes and literally just enumerate all 6 pairs and say, here's the distinguishing suffix.
So literally you have to go through any 2 pairs and prove
Yes.
that they.
Every pair you can distinguish.
Okay. And plus,